Okay, given matrix A, if I want to compute a to the fourth, a to the fourth is simply negative 212, negative 1, 5, negative 212, negative 1, 5, negative 212, negative 1, 5. So, oops, one more thing. Look at that. I forgot 1. What do you know? Negative 2, negative 1, 12, 5. So if I multiply those, that would be a 4 minus 12. 4 minus 12 is negative 8. And a negative 24 plus 60. Negative 24 plus 60. Well, you know what? Let me write them up. That's going to be a 4 minus 12 and a negative 24 plus 60 and a 3 minus 5 and a negative 12 plus 25. So this is going to be the same because it's the same matrix, right? That's going to be an 8. That's going to be a negative, what is that? 60, 40, positive 38. That's going to be a negative 2, and that's going to be a 13, right? Now I have to multiply those two. And that would be a 64 minus 2 times 38, 76. And 8 times 38, oh heck, 38 times 8, 64, 24, 304, plus 13 times 38. So that is, oh, you know what? I should have kept it the same here. Oh boy, I always say I'll go to the end. So that's 8 times 38 plus 13 times 38. And negative 2 times, that's negative 16 minus 26. And that's negative 76 plus 169. As you see, this is a lot of fun. This is negative 12. This is negative 38. This is a negative 393, and this is 13. That's 21 38ths. And as you see, this is a lot of work. So you could imagine if I wanted to do a to the 10, how much fun that would be, right? So here we come and say, all right, look, if I can take a and write a as the product of three matrices P, D, and P inverse. If I take a squared, I multiply this by itself, I times P inverse times P, that's the identity, they undo each other. D is a diagonal matrix, and when I multiply a diagonal matrix by itself, I get D squared. Oh, that's the part I forgot to show. Dang it. Yeah, I forgot. That's okay. I'll show you that in a minute. I'll show you that right after. And if I take a cubed, that's a times a squared, right? A squared is actually P, D squared, P inverse. Those will multiply, give you the identity, and D times D squared is D cubed, provided D is a diagonal matrix. So if I want to find a raised to any power, that's simply, it's going to always be P, P inverse, and you're just going to square the entries on the diagonal. Let me demonstrate. If I say a diagonal matrix is, I don't know, 2, 0, 0, 1. If I take d squared, that's simply 2, 0, 0, 1 times 2, 0, 0, 1. You'll notice that that's going to be 2 times 2. That's 4 plus 0, 0 plus 0, and 0 plus 0, and 0 plus 1. That's going to be 4, 0, 0, 1. If I take d cubed, that is 2, 0, 0, 1, 2, 0, 0, 1, 2, 0, 0, 1, and that is, I should have made that a different number. Let's make that a 3. So that will be 4 plus 0, 0 plus 0, 0 plus 0, and 3 plus 3. No, 0 plus 9. That will be 4, 0, 0, 9. And if I go for d cubed, well, this I already found. That is 4, 0, 0, 9. If I multiply that by 2, 0, 0, 3, I will get 8 plus 0, that's 8. 0 plus 0 is 0. 0 plus 0 is 0. And 0 plus 27 is 27. And do we agree that's actually a squared is the square of the diagonals, and d cubed is really the square of the diagonals? And if I wanted to find d sub 4, I simply say that's 2 to the 4th, 0, 0, 3 to the 4th. And you're not sure, multiply this by 2, 0, 0, 3, and you'll figure that out. So a diagonal matrix raised to a power is actually only the diagonal entries raised to that power. And you know where we're going with this. Given an n by n matrix, a squared matrix is diagonalizable if and only if it has n linearly independent vectors. That means it forms bases. Then, when you write it this way, D is a diagonal matrix if and only if the columns of P are linearly independent eigenvectors of A. So it's very important for this to work. Linearly independent is a must. Those vectors cannot be linear combinations of each other. In this case, the diagonal entries of a diagonal are eigenvalues, and the corresponding to the eigenvectors of P respectively. I'm going to show you a problem and work it out all the way beginning to end and show you how that works. For now, let's just make sure we want to get this. So instead of taking A and multiplying it by itself 4 times, I need to find the inverse, and we know how to find the inverse. That's 1 over the diagonal. 10 minus 9 is 1. Switch those, 5, 2, and multiply the non-diagonals by a negative. There it is. So if I want A to the 4th, that would be P, the diagonal to the 4th P inverse, provided those are, and they tell you that's what it is, provided these are the eigenvectors corresponding to eigenvalues. Let me recap. These are the eigenvalues corresponding to these eigenvectors. And I'll show you a problem really quick. So P is actually 2, negative 3, and negative 3, 5, multiplied by 1, 0, 0, 1 half, multiplied by 5, 3, 3, 2. Now that might seem like a lot of work, but imagine if you wanted to find this to the 400 power. The only work, this will be raised to the 400, this will be raised to the 400. So here, don't you only have to do to really satisfy this condition? Don't you just need to raise that to the 4th power? You know what? I want to make that a bit bigger. So don't you say take 1 raised to the 4th, 0, 0, 1 half raised to the 4th? So that would be 2 minus 0, that's 0. 0 minus 3 times 1, 2, 4, 8, 16, and that will be negative 3 times 1 to the 4th, that's negative 3 plus 0, that's a negative 3, and 0, 5 times 1 over 16, and you still have to multiply that by 5332. So, a raised to any power is simply the product of three matrices. That's about it. And that will be 10 minus 9/16, and that will be a 6 minus 6/16, and that will be a negative 15 plus 15 over 16, and that would be a negative 9 plus 10 over 16. And whatever that answer is, that would be, and let me see what that is. That would be 100. 160 minus 9, that's 151 over 16. 96 minus 6, 90 over 6. You could reduce those, of course. That is 16 times 20 minus 225 negative over 16. And that will be negative 90, 16, negative 90, negative 154, negative 130, 44, 34 over 16. Whatever that is. Now, here's another problem. They say, why don't you find us a formula for a to the k power? Well, this is p, this is d, and this is the inverse of p. So if I want to find a formula for the kth power, and notice how this plays, if I take a to the k, that would be p times 2 to the k 0, 0, 1 to the k, and negative 1, 4, 1, negative 3. And that would be 3 times 2 to the k plus 0, 0 plus 4, 2 to the k plus 0, and 0 plus 1 to the k is 1, multiplied by negative 1, 4, 1, negative 3, and that would be a negative 3 times 2 to the k plus 4, and 12 times 2 to the k minus 12, so that's 11 times 2 to the k, and negative 2 to the k plus 1, and 4 times 2 to the k minus 3. That would be the formula for any power of a. Now, really quick, if I take a, I just want to show you something really quick, and that's pretty much ties down many sections into one. Given a, this is a, given a to be negative 2, 12, negative 1, 5, if I take the determinant of a minus lambda I, that would be, let me do that right here. That would be negative 2 minus lambda at 12, and negative 1, 5 minus lambda. And if I do the product, that will be lambda squared minus 7 lambda minus that, no, not minus, I missed that. That will be lambda squared minus 3 lambda minus 10 minus a negative 12 is plus 12 equal to 0, right? And if I take this and say that's lambda squared minus 3 lambda plus 2 equal to 0, that's lambda minus 3 into lambda plus 1 equal, minus 1 equal to 0. And that would be lambda equal, oh man, 2 and 1, lambda equal 2 and 1. So if I say the diagonal matrix is 2, 0, 0, 1. So again, the lambdas are right across the diagonal. Do you see where they are? Now P is really fixed up accordingly. I would find P by finding the eigenvalues of each, meaning if I take lambda equal 2, then I come here and I say, well, let's see how this works. Then I'm looking for determinant of A not determinant. I'm looking for A minus lambda I equal to 0. So if this is 2, wouldn't that be right there? Lambda equal to negative 4, 12, and negative 1, a 2 in there, that will be a 3, right? So I could put it 0, 0, but isn't that multiplied by a negative 4, added, multiply row 2 by a negative 4, added to row 1, put the result in row 4? Wouldn't that simply make this negative 4, that's a 0, negative 12, that's a 0, right? So x2 is free, and x1 is 3x2. So x2 is free, and x1 is a 3. And do you notice this associated with the 2 is right there? So the first entry matches, and can you guess what the lambda of 1 is giving? It has to be in that order. If I let lambda equal 1, I'll notice that I'm looking at a negative 3 and a 12 and a negative 1 and a 4, and the same deal happen. If I work this out, multiply by negative 3, that's negative 3 and a 12 and a 0, 0, right? And that means x2 is free, and x1 is 4x2, so I will get x2, 1, and 4, and you notice there it is. And that's why eigenvalues and eigenvectors are so important. So if I really pay attention to this, when they take A and they write it as D is the diagonal with the eigenvalues on it, and P is the eigenvector for the corresponding eigenvalues, you just have to find the inverse, and you could take any matrix and write it as the product of P times D times P the inverse. And that turns out to be the key to solving matrices of any powers. Why do you need to solve matrices with powers? I'll demonstrate when we get there. So here's a problem. Let's see if we can follow this really quick now that you know the secret. The matrix A is factored into PD. Well, let's look at this. Guess what? You see that eigenvalue right there? Gave that vector. You see that eigenvalue gave that eigenvector, and do you see that eigenvalue gave, oops, color didn't change. Do you see that eigenvalue that gave that eigenvector? This is just you finding the inverse of this, which turns out to be the work, which is really minimal. In 5 and 6, matrix A is factored into P, D, P inverse. Use the diagonalization theorem to find the eigenvalues of A and the basis for each eigenspace. Well, we know that lambda equal 5 will really correspond to negative 2, 0, 1. We know that lambda equal 5 correspond to 0, 1, 0. And we know that lambda equal 4 correspond to negative 1, 2, 0. And those would be those will form the basis for the eigenspace. And if you watch the the Marvel movie, the last one, the Marvel what is it called, the War, and when they were trying to go back in time, right? Iron Man, Tony Stark said, ask the computer, give me the value of the eigenvector. applications are limitless. We're just doing the busy work, but once you start doing the work, you're really gonna enjoy this. Well, for a 2 by 2, they really don't give you the lambdas, but they give you that for a 3 by 3 to save you time. They say diagonalize the matrix in 7 through 20 if possible. The eigenvalues for 11 through 16, they tell you what they are. Here, if we want to really diagonalize this, we need to find first the lambdas. We take determinant of a minus lambda I and set that equal to 0. So we would take 5 minus lambda 1, 0, 5 minus lambda equal to 0. That would be 5 minus lambda square equal to 0. Lambda will equal a 5. Right? So if I now solve and put this in, if I solve a minus lambda I times x equals 0, that would mean I am taking 5 minus 5, 0, 1, 0, 1, and simply 0, 0. We really don't write this. The book doesn't. You could write it every time if you want. They just say, well, look, isn't that, if you multiply by negative 1 added to the next row, isn't that 0, 0? Doesn't that mean that we have x2 is 3? And the first one says, well, let me think. I lied. x1 is 3. And x2 equals 0, right? Pivots. So actually x1, 1, 0, this vector right here, any multiple will form the bases for what? It can be for R2. We have a problem, right? Since I can only get one vector and this is 2 dimensions, that's a contradiction. So what do we say? We say, since we cannot generate an eigenvector basis, oh my goodness, basis for R2, then guess what? A is not diagonalizable. So again, I should be able to find 2 linearly independent vectors for R2, 3 for R3, and so on and so forth. If I take number 10 and I do the same thing, and again, this is nothing more than figuring out the determinant of a minus lambda I equals 0 to figure out the eigenvalues, 2 minus lambda 3, 4, 1 minus lambda equal to 0. That is 2 minus 3 lambda plus lambda squared minus 12 equal to 0. Lambda squared minus 3 lambda minus 10 equal to 0. So that means lambda minus 5 into lambda plus 2 equal to 0. So lambda equal 5 or a negative 2. We have 2 values to really worry about, and let's see how this works. If I take lambda equal 5, I'm trying to solve the equation now, a minus lambda I times really x equals 0, or simply a minus lambda out, lambda, well, that's 2 minus negative 3, 3, 4, negative 4, right? It's really this. And that would be negative 3, 3, 0, and that's 0, 0, 0. So that means x2 is 3. And x1 equal x2. So here I'm getting this vector. I'm getting 1, 1, the corresponding vector to 5 lambda equal 5. And if I really would go ahead and take lambda equal 2 and see what happens, I'll be looking at 0, 3, 4, 1 minus 2, negative, oops, oh, I'm sorry, it's negative 2, negative 2. That will make this a 4, 3, 4, 3, right? So that is 4, 3, 0, 0. That means x2 is free, and x1 is negative 3 x2 over 4. So out of this, if I multiply by 4, it should be 1 negative 3/4. That will be 4 negative 3. They like fractions. They're really not going to write that as fractions. So I'll say P is actually corresponding to lambda equal 5. I will use 1, 1 and negative 3, 4 with a diagonal matrix of it. The order is very important. 5, 0, 0, negative 2. There it is. And now all what I have to do is figure out the inverse of this. And do I not find the inverse? Of course I do. The inverse will be 1 over the determinant. So 2 minus 12, negative 10. Switch the diagonals and multiply the non-diagonals by negative 3. There it is. That would be a negative 1 over 10, a 2/5, a 3/10, and a negative 1/5. So what do they want us to do in this case? They want us to take a matrix A, diagonals the matrix if you can. And the goal of that is for you to really be able to multiply them out. And I want to do one more. Number 14. And they tell me what the lambdas are for number 14. So for 14, if I really play with this, they tell me on number 14 lambda equal 5, lambda equal 4. They tell me lambda equal 5 and lambda equal 4. If I start with the 5 first, lambda equal 5, that would mean what? That would mean negative 1, 0, negative 2, 2, 0, 4, 0, 0, 0, right? So if I take the determinant of a minus lambda I and I row reduce this, that will be a 1, 0, 2, 0, 0, 0, 0, 0, 0. That means x2, 3 is free, x2 is free, and x1 is negative 2x3, meaning I get two vectors. I get x2 times 0, 1, 0 plus x3 times negative 2, 0, 1. So actually I get 0, 1, 0, negative 2, 0, 1. Those are two. That's very good because I need 3 for this to really work. Lambda equal 4. I will be looking at 0, 0, negative 2, 2, 5 minus 1, 4, and 0, 0, 1. And if I do the magic on this, I will get a 0, 0, 0, 0, 0, 1, and 0, 0, 0. Which means what? Which means x3 is 0, x2 is free, and x1 is free. So actually I messed up. That's a 1/2. My mistake. You can't get more. That I was like, wait a minute, what did I do wrong? x2 is 0. And x1 is free. So it's x1 times 1, 0, 0, which indicates (1, 0, 0) would be the basis for that eigenvector. So here I will say, let me put them in order. D is actually, I'm gonna write it as 5, another 5, and a 4. P associated with the first 5 is 0, 1, 0, with the second 5 negative 0, 1, and with the 4 1, 0, 0. And to find the inverse of this, I will have to work out the inverse. Diagonalize the matrix if possible, the eigenvalue. Okay, they give you the eigenvalues. Actually, that's all they wanted. They didn't say find the inverse. And there's your homework.